He's super toned.
Pardon?
He's super toned.
Yes. Tell them. Ready for all of that. I don't know what he's doing. All right, so start today.
Just throw me off. When they came off this one, they told me that you were going to be like, you
Never use the word tone in my presence. Ever. Ever. Never, 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 never use the word tone. Okay? Right? You may use the word lean. Lean is fine. You may even use the word skinny. That's fine. Not toned. Okay? We have two ladies and one on the thing, but in general, it's mostly, you never hear dudes say, I want to get toned. Right? It's mostly women that say, I want to be toned, which is going to lead us into this. Okay? Why? Because generally, the women think that they might get too jacked. They might look like Arnold, right? Women might look like Arnold. I'm going to be bulky, Dr. Black. Ugh, it drives me up the wall. Okay? So here's my question. All right? Let's talk about Arnold. We're going to talk about Jack. The real point of our bro science today is how big can you get? Okay? Naturally. Not the Arnold way. Okay? Not the Arnold way. But in a very, not taking anabolic steroids, how much bigger can you make your muscles? That's the question. Okay? If we were to go out and grab a random person, or it's Tuesday, so since yesterday was Labor Day, is today bench press day in the hub? Or do you think the bros got their bench in yesterday, even though it was Labor Day? I don't know. Okay? If we were to go ask one of them, how big can you get? What do you think? Pardon?
Because the limit does not exist.
The limit does not exist. Yes. Bonus points for a Mean Girls reference. Excellent. So, you can just get as big as you want. Do you think an average person, we were just to go grab somebody randomly off the street and we ask them, how big do you think they are going to say? You're like, I don't know. If I just work out enough, I can be as big as I want. I mean, there are probably people that think that, right? No matter what I do, I can be giant. Okay? So do you guys think that's true? No, right? Of course not. There is some limit, right? There is some limit that does exist. The question is, what is it though? How close are any of you or any of us to that limit? So, how big? Colin, what do you think? How big can you get? I guess we should ask, how big have you gotten in your life? When you first started lifting weights, how much? Like, how much did you weigh? And then what do you weigh now, if you don't mind sharing?
The heaviest I've ever gotten is 200.
Okay. 200. Okay.
202.
203. Okay. And when you started lifting, how big were you?
Probably like 160s.
160s. Okay. So, I mean, 30, 35 pounds. I'm going to divide 35 by like 160 really quickly in our head. What's that going to be? It's going to be like
22%.
how much?
22.
22. Okay. Did you get 22% bigger, Kelvin? I mean, you got 22% bigger, but do you think that's all muscle?
No.
I
wish.
You wish, right? Okay. So, what's the answer to this, right? And so this is the conundrum that we have. Like if you were to go and ask, I don't know, like we have a hard time. As soon as you start the conversation, people begin hedging, right? But it is, well, we're very close to it being football season. But the best part is when you get people like right after an off season, or in the middle of the off season, actually, the best are like, dude, like I'm thinking like message board football guy who is, like call in to the AM radio station, the sports animal, that guy, right? It's always the guy, it's rarely the girl. That person, right? So-and-so, he put on 30 pounds of muscle in one off season, right? You hear that all the time. Bullshit, okay? Maybe you put on 30 pounds. Maybe you did. It isn't all muscle, that's for sure, right? Also, you take a 17 or 18-year-old kid who may be more of a late kind of mature in that particular way, right? You get an 18-year-old guy that is probably, I'm sorry guys, y'all have peaked, okay? But they're probably at about the peak of their testosterone production, and then you get past 17 or 18 and it begins to decline, okay? Just wait, okay? Just wait in the midst of all of that. And some of them, they haven't eaten that much, they might be able to. Think a 30-year-old professional athlete going to put on 30 pounds of muscle in an off season? No. No, right? Absolutely not. And so most people think, there's a group of people who think, well, dude, if I just worked enough, I could look like Arnold. No, okay? The kind of flip side of all of that is there are, and it's mostly women that you encounter that are this way, that are afraid to do resistance training because they're afraid they're going to look like this, okay? They're not under any circumstances, okay? Or there's maybe like, a 1/10 of a 1,000th of a percent of them that might, but they're already, sort of more in that kind of inclined in that direction to begin, okay? So I'm sorry, Callie, but we cannot put you on whatever program we want and make you look like Arnold, okay? I know you're disappointed by this, right? And the other part of all of that is that in the vast majority of people, even if we were to go over there and look, right, the vast majority of people that do resistance training look nothing like this, right? Nowhere close to this. The vast majority of women that do resistance training look nothing like a fitness model or someone that's going to compete in a competition of those kinds of things, right? And so what I want us to take away from all of that is how big can you get? Not that big, okay? It's not that big. We can measure it and quantify it, and it's significant, and it is meaningful, okay? But it ain't gonna be this, okay? And so no matter how many like protein things the bros drink, no matter how many pre-workouts they have, how much creatine they have, how much they talk about their anabolic window, right? No matter how many times they go to CrossFit and flip over fucking tires and things, right? While not socially distancing and everything else that's going on over there, okay? They're not gonna get that big. So here are data. This is real data from a big study, okay? Almost 600 people in this study, okay? It was done across multiple sites. It was done at UMass Amherst, at Yale, and at Boston University, I believe were the 3 sites. And it was run out of Priscilla Clarkson, who's no longer with us, but she was a very famous exercise physiology professor at UMass Amherst. Tom Price was at Yale. Tom ran it out of the Yale's thing. And Monica Hubel, who was one of the authors, was actually here and spoke last year, the year before last, maybe in the spring. She was our kind of outside speaker that we had that came in. But the point is, this is 12 weeks of progressively changing, well done. It's just single arm bicep curl, okay? 3 sets of 12 for the first month, the first 4 weeks, 3 sets of 8, 3 sets of 6. I believe every month they reassessed 1 rep max so that they could make sure they were continuing to work out. I believe at 12 it was like 65% of 1 rep max. At 8 it was 80, and 6 it was 85, something kind of right about there. And they reassessed, so they were doing about as well with that, with a reasonably kind of not huge volume as we can get. Okay, and this is a histogram of the number of people. So the percentage of their almost 600 people, it's broken down. We've got men and we have women that are going to be on here. If I look at all of these things, I'm forgetting which one is which. I think I think the women are in black and the men are in white. That could be wrong. But this is just kind of a histogram. Look at this. You guys talk about normal distributions yet in stat class? Normal distribution, right? We've got a mean. Our median and our mode are all going to be probably pretty freaking close to that. We're going to come off on our tails, okay? All of this. There were a couple of people that got smaller. Smaller. There were a couple of people that got like 50% bigger. I should tell you that they took MRI images of their biceps. That was how they quantified this. So this is as accurate as we can get this to be. Okay. So the vast majority of people, right? We're within plus or minus a standard deviation. We're about our 2/3 of people are probably going to be somewhere in this kind of 10 to 20% range. Okay. Maybe like 8 to 22 or 23% range. So if you say on average, the average person over 12 weeks is going to get like a 15% increase in muscle size. I think I did this in the undergraduate class. But you take a 150-pound person with 15% body fat. You increase every muscle in their body, every one of them, by 15%. They've gained 8 pounds. Okay, 8 pounds. There's no way you're going to make every muscle in your body get 15% bigger. Okay. Some of them aren't going to get bigger at all. You probably have a better chance in your biceps of getting things than you do like in your gastroc and your soleus because you're walking around on those things all day. They're already taxed out. Okay. So, how big can you get? Not that much bigger. Is 15% noticeable? Were your clothes fit differently? Right? Right? You're going to have some real schmeekium shirt on or something. People are going to notice that? Maybe. Okay? I see all kinds of weird things. All right? So, ladies, apparently, like burying your midriff is back now. People walking around that way. I don't know, it kind of freaks me out. Okay? Dudes never really changed their stuff much. We just, shirts cut out like down here. Those kinds of things. So. Okay. So how big can you get? Not that big. 15% in women, right? You take a 120-pound woman and she's gonna get 15% bigger. Like she might gain like, if it's just muscle, maybe she gains, 4 or 5 pounds, right? Tops. That's if you're doing total body stuff. So she was 120, now she weighs 125, but she's probably not she's probably not a 6 anymore. Now she's 4. It's just, it's not that big. No one's going to be that big. So that's my pitch. Not going to get that big. Okay. Anybody have questions about that? We spent the entire class like taking a quiz and talking about bros and lady bros and all those kinds of things. All right. So the next piece of things in class, this is my favorite thing. Okay. I'm not gonna lie, we'll spend probably 3 good, nearly full class periods talking about all of this because I think it's really, really important for us to kind of understand how everything fits together. And so what we're going to do is we're going to take this piece by piece by piece, and then at the end, we're going to circle back and try to fit all of these pieces together in some more applied examples. Okay? So the idea is, what is it that controls how much force your muscles are able to produce? Okay? And so generally, like I taught in my undergrad class, like last week, look, it's basically how big are your muscles, it's muscle size, and of that size, how much of that muscle can you turn on or recruit at any one given moment in time, okay? Bigger muscles, larger ability to turn that muscle on or get near turning all of that muscle on, the stronger you're going to be, okay? That's not wrong, okay? But it's not the whole story. There's other things that we have to consider in the midst of all of this, okay? And it becomes really, really apparent when you do any sort of laboratory testing, oftentimes like what we do in my lab, when people come in and you're like, how is this little small person able to generate so much force, okay? And then we get some, like these bigger, larger people, and they can't generate, nearly as much. And it's this kind of really, really obvious dichotomy that it's not simply just who is or who has the largest muscles all the time. All other things being equal, sure, having bigger muscles matters, okay? Having bigger muscles matters. But, it's not the whole story, okay? So what I would usually do at this point, if we could get closer together and we could do some other demonstrations and things, is I'd pick somebody, we'd get out some weights, right? And we'd see how much weight they could lift, and we'd pick somebody else, and we'd have them do some weights, and we would look at, okay, who is stronger? Who could curl more? Or we could bring a barbell in here, like who could deadlift more or something, when we get into trouble, right? So we're going to throw their back out in the midst of all of this. And we would talk about, okay, why do we think this is the case, right? So why could Alex lift more than Kelvin, right? Why can Megan lift more than both of them, right? In the midst of all of this, right? So if I ask you though, we're going to start off kind of with this. If I ask you to pick out who in the classroom you think is the strongest, okay? You look around at everybody. What is going to be the thing on which you might base that kind of just initial surface level decision? Kelly, what do you think? You don't have to tell me who you think would be the strongest, but on what might you just be making that decision? Probably size, right? Okay. You look around and you think, okay, well, who's got bigger muscles? Okay, or who has bigger muscles and maybe they look a little bit more defined than somebody else or something. Right? We're looking at appearance of these things. And so that's the thing that most people think about. And it's not wrong, okay, but there's some other things that are going to go into that. You guys know anybody, like any sort of large individuals with big muscles that are actually not very strong? Tilden probably works with them almost every day, okay? Poor Aaron tested some of the basketball players as part of his dissertation, and I promise you that we have untrained kids in our classes that can have better quad strength than those basketball players did. His numbers were astoundingly low. And part of it is they're long, they got this long levers, and the way our chair was set up, and there was some weirdness to some of those things. It's not always kind of what we expect, okay? But in this instance, size does matter some, okay? But within that size, okay, we need to understand that muscles and their size are going to exist not only with different sizes, but also with different shapes contained within that size. You may have muscles that are short and thick, like your quads, long, slender, kind of rope-like muscles like your hamstring, okay? In a very general sense, the longer a muscle, the faster it can contract, okay? We call this, in long muscles, we have individual sarcomeres that are going to occur in series, okay? We have sarcomeres in series, sarcomeres in parallel. Ugh, I'm losing my mind, okay? But if you've got sarcomeres that look like this, one muscle, and then you have sarcomeres that look. This muscle that has this number of sarcomeres, right, that are running parallel to each other. These are going. This muscle is going to be faster, have a faster contraction velocity than this one. You don't want to get into the physics of all of this, or the kind of hows and whys. Just trust me on all of this. Okay. So this one is, we'll just say faster, and this one will be slower. Okay. Additionally, if we increase the cross section, we're going to get an increase in force. So in this example, we have the cross section of these muscles is the same. It's 1 sarcomere wide, okay, but this one's 4 sarcomeres long, this one's 2. I'll just draw this one here. If we do it this way though, okay, sarcomere, sarcomere, sarcomere. Got 3 versus 2. This is a larger, what we would call cross section. These are sarcomeres stacked next to each other, not running in parallel, running in series. And so in doing this, okay, cross section is bigger, they're pulling in the same direction, you've got a wider spread on this. This is going to be stronger. This one is going to be a little bit weaker. Okay? That's the general kind of starting point for everything. Right? So just think, big, right? Big bulging biceps, bigger cross section. Okay? Hamstring long and thin. Okay? Hamstring long, quad short. Okay? Hamstring can contract faster than the quad can. The quad has more of this. Okay? So that's our starting point. Now within all of that, there's going to be some differences. There's going to be some other things that are going to happen. Okay? So these pieces of steak that you see here are, that's my quad from when I was a grad student. These are images, some kind of pre-images from part of my doctoral dissertation. Okay? You are looking up through the feet. Okay? This is my left leg. So you're looking, my leg is coming out at you. You're looking up through my feet. This is the vastus lateralis out here, rectus femoris, vastus intermedius, medialis. This is bone marrow. This is the mineral part of your femur here in the black. Okay, the femoral artery is right there. These are some hamstrings. I don't really know which one is which because I've never had anatomy and I don't really give a shit. There's a gracilis in here somewhere. We got abductors and adductors and other things that I don't really care about. Okay, the white stuff out here, that's subcutaneous fat. Okay. The reason it's kind of pinched in here, there and there, is we crammed my leg into this little coil, this little box thing that you put around your muscle when you get into, this is a much more high-powered magnet, like an MRI, than what you like go to at the doctor's office. And so the resolution is better because the coil helps you focus the magnetic field in there a little bit better. So, in general, we're going to say strong, stronger, strongest, right? This is a cross section, just right through my leg, okay? Bigger cross section, stronger than smaller cross section. It's not exactly that, okay? Within this, if you look at the quads, okay? Quads, here the 48 extensor muscles versus the hamstring muscles, okay? Even within that actual cross section, there's going to be some differences in the arrangement of the muscle fibers relative to the tendon to which those muscles connect. Okay? This is very often referred to as muscle architecture. Now, we can make this super duper complicated, and as a person that tried to publish a paper making a few kind of very rough calculations about muscle architecture, I can tell you there are some reviewers that are very, very persnickety about how one goes about doing all of this, and I hate them. So the point, though, is the fibers that are contained inside of those muscles are not always going to face exactly the same direction in every muscle. And the arrangement of those fibers, okay, is often called pination, right? So we may have, this is the example here is calling it the sartorius muscle, okay, which is an abductor or an adductor. I don't remember which one it is, okay, but think of it in some ways also like your bicep, okay? It's what we call fusiform. In your mind, you probably think muscles look like this, right? All of the muscle fibers in like my bicep are running almost exactly parallel to the line of pull of the tendon. So I have a biceps tendon, right? And it's going to come down here and it's going to make an attachment on, I don't know, the radius, one of those two. I know there's at least two of those bones are down there, okay? And so then when the bicep shortens, the tendon shortens and it pulls your lower arm, okay? So the tendon pulls this way, the fibers pull that way. So they're all running like exactly in line, like a regular tug of war, okay? They're doing this. Nice and easy. In these fusiform muscles, okay, where the fibers run parallel, essentially every bit of force produced by myosin in those muscle fibers, inside those sarcomeres and those fibers, is going to be applied directly onto the tendon in the same kind of line of where we need to generate force, okay? So in that way, fusiform muscles are very efficient at the transmission of force from myosin or from the sarcomeres to the tendon, okay? But the problem with this, okay, is that because of this particular arrangement, we cannot jam as many fibers into that area as we can under some other circumstances. And so what tends to happen then in some other muscles is we have something where the fibers are going to come in at an angle. So here's what we would call a unipinnate muscle, which is the semimembranosus, which I think is a hamstring, right? Membranosus, tendinosus, yeah, those are hamstrings, okay? The rectus femoris, which is one of your knee extensors that runs right about here. That one I do know, okay? The deltoid, which is here, okay? So we have unipinnates, they're all coming in from one direction. Bipinnate, they're coming in from each side like this. Multipinnate, there's going to be multiple little pieces where the tendons are going to all kind of mush together here. And so each one of these is going to have its own kind of unique thing. Then like the pecs are going to be these triangular ones. And so what happens with pinnation as we move off of kind of straight on pull is we have to go back to physics. I'm sorry about that, okay? But it's the same idea that if I want to push the desk at Callie, but the most efficient way to do that is to push it directly at her. However, okay, if I'm off at an angle over here, and remember, a fiber can only shorten or lengthen in one kind of direction, okay? All that if I'm over here and I'm a fiber, all I can do is push or pull exactly in front of me. So if I push, what you will note is that it has moved towards Callie, but it has also moved some towards the wall over there, okay? And so that is going to require us, by coming in at that angle, we have to go back to physics and remember something called vectors, okay? Now, everybody hide under your desk, okay? Vectors, math, right? Trig, calculus, differential equations. Yeah. Pearson, have you had differential equations?
I have.
Yeah.
It's one of my least favorite classes.
Yeah, so it's okay. You're probably the only one in here that's had maybe anything more than, anybody have, you in Cal 2? No? So my college roommate, one of my best friends in the world, he was a physics and engineering kind of double major. And so he would laugh at me when I was taking physics and it was kind of the trig-based physics. And he'd be like, no, but if you do it with calculus, it's way easier. I'm like, shut up, dude. I'm like, no one cares. Right? Like I appreciate how we can, you know, we can use derivatives and calculate accelerations much easier and all of these things. I'm like, I'm having a hard enough time with all of this. So, okay. So when we have pinnation, okay, and even muscles where it's fusiform, where they run in the same direction, they still have they have pinnation. The pinnation is just zero, okay? The idea of this muscle architecture and this idea of pinnation brings up something called physiological cross-sectional area, okay? If we want to use the size of the cross-section to get the most accurate prediction of how much force a muscle can generate, we need to use physiological cross-section, if we can calculate it, rather than what's called anatomical cross-section. When I showed you guys those MRIs of my quad, if you just circled the individual muscles, like we just sliced right through here, circled those, calculated their area, that would give you an anatomical cross-section because it's doing nothing with the arrangement of the fibers that are going to be in there, okay? In muscles that are fusiform, like your bicep, like some hamstrings, a little bit, like your abductors and adductors, in fusiform muscles, physiological cross-section and anatomical cross-section are equal. Okay, the closer your pennation is to 0, then the closer physiological and anatomical cross-section are going to be to each other. Okay? So, to calculate physiological cross-section, we need to find a way to represent the sum of all cross-sections, okay, regardless of what their pennation and their complexity is going to be. So let me show you how this, in some ways, can be done. Okay? If we are able to dissect a muscle and weigh it, okay, we can get a muscle mass. If we can do these things, we can dissect it, we can pick out exactly what the pennation angle is, we can measure fiber length, and we can calculate that physiological cross-section is equal to muscle mass multiplied by cosine of our pennation angle divided by the density of a muscle multiplied by our fiber lengths. You're looking at me like, well, Dr. Black, how the hell do we care about muscle density? What does that matter? What about fiber length? All of these are things that we can actually measure in an intact human, so why do we care? Well, in people, okay, the way that we get at this basically is that physiological cross-section is cross-sectional area multiplied by cosine of pennation angle. That's the easiest way for us to make some approximation of this. And I will tell you that actually, rather than using cross-section, if you use volume of a muscle rather than the simple cross-section, you get volume multiplied by cosine, you actually get a better approximation. Okay? That was part of the paper we were trying to write and those sorts of things, but the reviewers were very upset with us. Because we were trying to use estimations of pennation angle from cadaver data so that we could account for all 4 muscles, not only the quad, not just the lateralis that you can measure with ultrasound, which I'll show you guys. We were using cadaver estimations of fiber length. They didn't like that, and so we kind of got mad at each other. Okay? But what we're trying to do is to take some measure of a cross-section, and then if we have cross-sections at sort of various kind of intervals up and down a particular muscle, okay, we can then do a couple of other things and try to pull out something that looks more like this 3-dimensional muscle in an effort to let us get a better estimation of, given the size of your muscles and the pennation of your muscles, we can predict, if we know those things, we can better predict who's going to be stronger than somebody else. So that may in some ways account for why some people that appear to have smaller cross-section because of their pennation angles may actually be stronger than somebody that has a larger cross-section. Does that make sense, guys? So, again, I am listening to this book about the Iraq War and known unknowns and unknown unknowns and unknown knowns and things. But to better approximate physiological cross-section, we have a couple of other things that we need to measure. So we need like an MRI measure or something to kind of guess at what your actual cross-section is. And then we need to be able to measure pennation angle. And so on relatively superficial muscles, we can take ultrasound, which we have downstairs. We have the good ultrasound machine that is Dr. Kellowan's, and then we have we'll just call it less good ultrasound machines that are Dr. Mike's. Okay? And so really to be able to try to image and get a good estimate of pennation angle, this is really, really easy to do on superficial muscles if you've got a good ultrasound machine. We would use Dr. Kellowan's. Okay? And we've done a couple of studies. There have been a couple of master's theses. There was even, when Ade was here, there was even a senior capstone project where they did this. What you do is you put the ultrasound probe out here on the lateralis or here on the medialis. Can't really get the intermedius, but you can get it on the rectus femoris, okay? On these superficial muscles. And what you can see is this here, this is skin and what might be subcutaneous fat, okay? This is what we call the deep aponeurosis. This is connective tissue. So This muscle here is the vastus lateralis. This is the outside where your skin is. This is the deep aponeurosis that's going to separate the lateralis from the vastus intermedius. And if you run this parallel, what you see is these stripes that look like this. That's the angle. Those are muscle fibers. They're running in that direction. Okay. And so what we're really seeing here is probably a fascicle and not an individual muscle fiber. Okay. But you can just simply save a picture like this, export it, slap a protractor on here, and look at these things, and you can measure then the cosine. This is your pennation angle. So this, in theory, is part of the deep aponeurosis that's going to at some point become tendon. So these things are trying to pull in this direction. The tendon runs like this, so they're coming in at this particular angle. So when they pull, they're trying to pull the tendon this way, but also up that way. And so we can measure those things. Okay? The shallower that this angle is, so the more that these fibers are going to come down, down, down like this, okay? The smaller the angle is, the closer the cosine is to 1, which means that almost all of the force being generated through these fibers is going to be directly applied to the tendon in the direction of pull. As it goes this way, it takes up, 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 up like this, then the cosine is going to get farther. As the pennation angle gets bigger, cosine gets farther away from 1, gets smaller. So less of the force will be directly applied in the line of pull with the tendon. Okay? Pretty easy to measure these guys. Go.
I can't remember if I'm remembering this right, but with training, you can decrease pennation.
Is that right? I know that training can change it. I was thinking to increase it, but that wouldn't make a lot of sense, right?
Mm-hmm.
I feel like the training increases it, but I'm going to show you why that might still actually be a beneficial thing in just a minute. There's several papers. We could Google it really quickly.
It says increase.
Does it? Okay. So let me show you guys now how we take an image like this and we try to calculate physiological cross-section area. And then it may make more sense to you guys why, when we do training, especially like in quads, why angle may steepen. And it may go from like 22 degrees to 28 degrees or something. So I mean, and the math on all of that is just a couple of percentage points that I use. So
Would it increase from like the like hypertrophy of the muscle? And okay, I couldn't remember if I was remembering if it was increase or decrease.
because what's going to happen is, if you, in this picture, imagine that each one of these things is an individual muscle fiber, even though it's really not. If each one of these things gets a little wider, it's going to start shoving all of them in these other different kind of directions. And so you're going to basically stack more stuff in here than you had before. And that's going to tend to push, because it can't push down, it's going to tend to push things up a little bit. But then the top part, it's going to actually expand, okay? And so what you've got, okay? Fusiform muscle, physiological cross-sectional area is equal to anatomical. To calculate physiological area, what we need to do is, here we have fibers that are coming in. We actually have to cut across these fibers so that we can figure out what the 90-degree angle of pull is going to be. So that this one has this much space, okay? But this pinnate one has, like 4 times as much. So we've got 4 times as much muscle pulling on that tendon, okay? Even though we're losing some of the force because it's that way, we've got 4 times as much actual size there. Then if you have these multi-pinnate, this is like a bipinnate muscle, the physiological area is then twice what it is there. So you can imagine that what's going to happen is when I get hypertrophy is that, yes, these things may steepen a little, but this is going to expand out enough that we're going to actually increase. We may lose a little bit of pennation, force from pennation, but we're actually going to increase this perpendicular area even more so. And so the hypertrophy certainly well overcomes that change in pennation angle. Okay? There have been studies on, do sprinters and endurance athletes have different kind of innate pennation angles in certain muscles, et cetera, et cetera, et cetera. And per your muscle size, is a certain pennation angle going to be better for speed? Probably. Right? Probably a little shallower, maybe better for speed, but that's kind of how this all works, okay? But again, this is a concept. We can calculate these things. In theory, we could take a couple of CT images downstairs in Dr. Deb's lab if she will let us, okay? And then we could take the ultrasound machine, we could measure pennation angles, right, in the midst of all of that. And we could roughly try to approximate something that looks like what this is, and then use that in a regression equation or a correlation to be like, okay, you're going to all come in and squat, or you're going to all come in and do knee extension, and then we'll try to predict then from that which thing does the best job of predicting who's the strongest. Okay? Now, there's some other things that are going to go into all of this as well. But this isn't done that often, but it's something that we can do, and I want you all to appreciate that it does exist, okay? That things are more complicated than just, right? That Pearson has a bigger quad than Megan does, and so we would imagine he is stronger, okay? That may very well be the case, but it may not be, okay? And that's what you're going to kind of have I thoroughly confused you guys yet? Alex, you okay? Sure? Okay. Did I tell you guys last week that I read something that said that one of the huge consequences of the pandemic and of the masks, the easiest way for you to feel better at any point in a given day is to either smile yourself or have someone smile at you? Did I tell you guys that? I think maybe I told the undergrads that. So what we all need to do is, in a very like I'm the Joker kind of way, like we need like a sticker or something to put on our face mask so that it looks like you're sort of like smiling or something. We're losing that though, right? You're just like, here, you don't have to smile at people because why would you want to do that? Like they can't tell if I'm smiling or not. So anyway, so maybe we all need to like spread out and be like, once a day, like pull your mask down and smile at your neighbor and say something nice about them. Tell them you're happy to see them or you're hoping they're okay or something.
Well, it's kind of that seems creepier.
Right? It's a little creepier, right? It's a little creepier, but I'm just, you know.
You can smile with your eyes.
Can you though, Calvin?
Well, in the Power Bank, you can. See? It's called smile. Oh.
But the question from all of that is, are people in tune as easily to that as they are? Like, are we going to get the same psychological kind of, are we still going to get dopamine out of that as we are from the other kind? I don't know. Anyway, I thought about that, you know, with Alex and his like black mask. I'm like, oh, we could just like, you know, get some chalk and just put a little smile on there, right?
Just get research departments that get communicator masks, the ones that have like the plexi on them, you can see that deaf people read lips, so if you
Right, like we need a mask, but it just needs to just like let it be clear. How hard is that?
I didn't think of that.
yeah.
Clear fabric or something.
I think that'd be the right for another person, like you need to have a mask that shows your mouth.
They can't look at it. I saw her changing with the face shield on today. She was wearing 2 masks and a face shield. And I was like, ooh, her face shield. I don't need one of those face shields. So, but apparently just wearing, like if you were not to wear a mask, that wearing the face shield is better than nothing, but it's not nearly as helpful as wearing a mask because there's still like plenty of airflow. It's good for like spatter and those kinds of things.
I didn't think we had enough space.
I was like, two.
It's like a bowling ball rolling around somewhere.
Like the
Okay.
range with a catch.
So I'll start this and then we'll do about 10 minutes and then we'll call this good, okay? So in some ways, what we've talked about is the easy part. What we just talked about is the easy part of force production. Okay? It's muscle size, it's physiological cross-section area. How much muscle do you have? Okay? The significantly more complicated portion now is, so you have some size of a muscle. So you have some physiological cross-section area. Now we're down to what can you do with that muscle, okay? And it doesn't do us any good to have a really big muscle if we can't actually engage all of that muscle or all of that physiological cross-section, okay? So the process of turning on a muscle, getting it to contract, is called motor unit recruitment. I'm going to put activation on there. Let me tell you, much like the physiological cross-section area calculation things, the use of the word recruitment versus activation and which denotes precisely which, in which context, is also very hotly contested, and people get super persnickety about it. Anybody that's had an undergrad in all of this, the difference is kind of like the difference between is it a VO2 max or is it a VO2 peak, and damn it, if you know, pool's not going to call it a max until you put somebody's ass on the treadmill twice and like validate it, and you're clearly, anyway, there's some, when we turn a muscle on, I'm going to refer to that as motor unit recruitment, okay? We turn the muscle on one motor unit at a time, okay? And this may seem like a very inefficient thing, but it happens so quickly. So you may have, in my bicep, I may have 2,000 motor units. So I've got 2,000 motor neurons in my spinal cord that go to my right bicep, okay? And that those 2,000 motor neurons may innervate 15,000 individual muscle fibers or something, okay? Those are just wild speculative guesses, okay? But what happens is when we need to turn on the bicep, the point of all of this, okay, we'll start kind of at the end. The point is we need to be able to very, 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 very precisely turn on just enough muscle to get just the right amount of force for whatever task it is that we're doing, okay? I need to be able to pick up this marker, right, and not throw it behind me. I'm serious, but if I generate, like if I need to pick it up like this, if I generate and I overestimate the number of motor units to recruit, I get more force than I need, and that's going to want to forcibly like throw it behind me. Okay? If I generate too little force, it's not going to move. And so just imagine every time you do anything, you write, you talk, okay, you smile with your eyes, apparently, how we're supposed to do all of that, okay? You're doing squats. Every time you step, okay, you're very likely contracting multiple muscles at almost exactly the same time, all of which are producing just this very, very, very precise amount of force to allow you to generate this motor pattern, okay, or this movement pattern that we need. You couldn't write if you couldn't do this. You just like jam your thing into the paper, okay? All of this is very well illustrated in some ways when you have a toddler at home, right? Like she's getting better, but like she can't write. She grabs a crayon and she can sort of make these very gross movements, but she cannot, even if we could explain to her what we wanted her to do, she doesn't have the, kind of the fine motor skills yet to generate that little precise changes in force production that we're able to get by, one extra motor unit on or one extra motor unit off at various times, okay? So this ability to turn them on and off is controlled solely by the central nervous system. That's not true. Under almost all circumstances, it's controlled by the central nervous system, okay? When you activate a reflex or something, then it's not really controlled by the central nervous system, depending upon if you want to classify the motor neuron itself as being part of the central nervous system. There's debate about that too. There's debate about everything because we're researchers and we're never happier than when we're trying to parse the language down to make our idea seem a little better than somebody else's idea, because that's life. Okay? But recruitment is controlled by the nervous system. We turn fibers on one motor unit at a time, and that's turned on according to something called the Henneman size principle of motor unit recruitment. If anybody needs trouble, anybody's having trouble going to sleep at night, I will give you the Henneman paper and you can read it and you will immediately go to sleep. Okay? In that paper, this is one of the fundamental things of all of sort of neurophysiology. The size principle of motor unit recruitment, or the size principle of which neurons will depolarize first. You might be shocked to learn that if you read the paper, that is mentioned like as an aside in the paper. It's nowhere near the point of the experiment. The most famous thing in that experiment that everybody talks about in every physiology textbook ever wasn't even the point. Okay? Sometimes we luck into things. Right? You never really know what's going to be a big hit. But the smallest motor units, and by small I mean the motor units that have the fewest number of muscle fibers in them, are the ones that would be recruited first. Okay? So when I need a small amount of force, I will generate, I will recruit my smallest motor unit in that muscle. It will get turned on first. If that does not generate enough force, I will then recruit a second motor unit. Okay? It will be the second smallest one. And I proceed up in that manner until I have recruited or turned on enough motor units to turn on enough muscle to get enough force to do whatever it is that I want. Okay? Sadly, that's only like half the story of that. We'll get into the rest of it, okay, on Thursday. I want to make one other point, though. Okay? One other point. The smallest units are turned on first. I also want you all to remember, though, this is really important, is that the size of the motor unit, the number of fibers in a motor unit, is generally governed by the fiber type of the fibers that are contained in that motor unit. So small motor units tend to connect to slow twitch muscle fibers. Okay? And so it's going to go slow, 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 slow. And as the motor units get bigger, then we're going to begin to transition into 2A. We're going to get bigger and bigger and bigger. We're going to transition into the 2X's. Okay? So we're in a pattern of things that, from a functional standpoint, anytime you do a common activity like walking or things, the smallest motor units in that muscle are going to be recruited over and over and over and over again. They're recruited during almost every contraction. Okay? When you're walking, you're using roughly this, if it's level, right, and you're going at kind of a low speed, you're using roughly the same motor units every step that you take. Okay? And so there's some consequences to this that are good and that are bad. The primary thing that is good about this, what are type 1 or slow twitch fibers? What are they good for? They're fatigue resistant. Okay? And so what that means is that if they're the ones that are always getting turned on first, that's good because it's going to be more difficult for them to get tired, for them to fatigue. So I can walk and turn on the same ones over and over and over again, but I'm not really going to get fatigued just from walking. Okay? And this is kind of a chicken or the egg sort of thing as well, right? Like, it's good, but also then those ones that you use over and over again to walk are also getting a training stimulus because you're using them over and over and over again. And so it kind of perpetuates this sort of same cycle of things. Okay? But that's the basics of this. What's going to really freak you out on Thursday is that the nervous system is like an old computer. Okay? You guys know what analog signals versus digital signals are? Anybody ever heard about that? My engineer, analog, digital, anything?
Yeah, but I don't know the specifics.
One of those specifics, okay. So like analog is it's on or it's off, right? So you get a 0 or a 1 like in your code basically or something. It's on or it's off, okay? You get an action potential and it depolarizes or you don't. Okay? Yet, once it's on, we actually have some level of ability to control the extent to which it's on. Okay? And we'll talk about kind of how we can alter that and some of the unique properties of the motor cortex and how a lot of that is sort of taken away from, it's taken out of the hands of your brain because it's too complex of a task. Like, can you imagine you're walking? You don't think when you walk, ooh, okay, this number of action potentials to my lateralis, this number to my rectus femoris, this much to my soleus, right? It's just walk. You kind of know how to do all of that. And so the brain is just dumping this signal out. And the spinal cord is going to function in a lot of ways to help kind of modulate that. And then we do a lot of cool things like I'm walking and I walk by and Callie tries to shove me and she knocks me sideways and I can immediately change which muscles are on and to what extent they're on and alter my force pressure so that I don't fall over. Sometimes. I walk back there and Alex tackles me, I'm kind of screwed. Right? So we've got this really, really complex, but also not so complex way of controlling. Not just is it on, but to what extent is it on. Okay? So we'll stop there for today. All right? Make sure your quiz is up there. We will not do critical thinking on Thursday. So you don't have to have your critical thinking questions ready. It will probably be next Thursday before we're really ready for critical thinking. You need like 2 good days to